Welcome back to the channel. In today's video, we're going to continue in our Python for Forensic Chemists data series. Now, over the course of this series, the emphasis has really been on how we can extract more information out of our data at every point in time. If you look at the past videos, we use the standard normal variate to get more information out of our near-infrared spectroscopy data. We then took a deeper dive into the metadata to get more information out of that and using that to understand our overall data set better. We then went a step further and using hoteling t-squared so we can actually understand the multi-dimensional variation of our data set. So here we combined our PCA with this additional hoteling t-squared property so we can actually see how tight our clusters are and understand the overlap a little bit more. Now in this video, we're going to look at the impurity of our cocaine samples and take this similar type of approach where we're not really going to build a sophisticated model, but more so try to understand the output of that model better so we can understand where it's performing well and where it's not as we continue to try to extract more information out of each process. So let's get started. I have already imported a number of libraries that we'll need for this particular video, and I have already set up some of my variables. So we have our Y data, in which case we're going to be predicting the impurity. So if I run this cell, you can see our impurities are caffeine, levamisole. One way to look at all the variables is to use the unique method, and you can see we have our unique variables. So these are all of our impurities, and then we do have pure cocaine in this case. And then we are using the X data, which is our standard normal variate scaled NIR data, which includes again some of the visible information as well. This is on a lab-based visible NIR spectrophotometer. So let's get started. The first thing we want to do is build our actual model. And again, I'm not looking to build a sophisticated model, but we will use this make pipeline method in order to put together the steps for this model. So we'll call our model pipe, and we will use the make pipeline, which allows us to stack multiple techniques together as we build our model. So the first technique we will use is standard scalar, and we can just import that. And we could just use that. Here we imported it there. And then in the next step, we will use logistic regression. And so we're not going to do much by way of optimization, but in order to ensure that it runs fast and converges, let's just set the max iteration to 1000. And we can set the n jobs equal to -1. This might slow the overall computer down, but it does allow for more compute resources for this model. So if you notice your model's running a little bit slower, you can sort of tweak the number of jobs that you allow your system to use. The next thing I want to do is now fit this model. So we can fit our model on the data. So as part of our extra due diligence, we're using train test split so that we can train the model on some of the data. In this case, we're going to use our X train and Y train to fit the data. We're using a random state of 4 and a training size of 75%. So most of the data will be used to train the data. The last quarter of the data will be used to test how well the model performs. So to do this, we'll just simply use X train, Y train, and this is where the model parameters are estimated. And we run fit, and we get this pipeline object. And so we can see everywhere to actually grid search and optimize the model. We would get that, but we can see the parameters we've passed into the model. So the max iter, the n jobs. There's a regularization term we could have used. The C term we could have optimized. We could have changed the penalty. So there are things we could do to improve the model. And there's many videos on this topic. I have a few on this channel. However, I want to focus more so on the model output. So let's take a look. Let's look at how our model performed on the training data. So this would give us our training accuracy. We can just pass in X train and Y train. And if we look inside this method, we can see that it will transform the data and then apply score with the final estimator. So in this case, we're going to compute the accuracy of our model by passing in our Y train, our X train and Y train, and it will return the score as a float. And so if we look at this, we have a training accuracy of 1. So this model is essentially memorizing the entire data set. It's able to find the patterns and is doing a great job. However, let's look at our test accuracy. And this is the data we held out in that first cell. So this is now where we're able to use X test and Y test to see how well it performs on out of sample data. And so here we can see our model has a test accuracy of 86%. So these are the samples that were not used to build the model. Is this good enough? Really depends on the context. Maybe it is, maybe this is as good as a human could determine or as some expert in the field could determine. That's really how we know. In most real life scenarios, 100% accuracy is not a given, and 100% accuracy may not actually be attainable depending on the situation. This is the case in many, many areas. However, what we want to know, and this is the focus of this particular video, is, well, what is it getting wrong, and can we try to understand those inaccuracies? And looking simply at the score doesn't help us, because essentially what this model is trying to do is determine, if we go back to our xtrain.unique, it is trying to predict the likelihood that our impurity is lidocaine versus the rest of the samples. And so it computes a probability that it's lidocaine, that it's mannitol, that it's inositol, and whichever one has the highest likelihood is the sample that it would predict. And so let's see where it's getting it wrong. Maybe it's a low confident output. And so to do this, we can use a confusion matrix. A confusion matrix allows us to determine, well, what the predicted label versus the true label. And in an ideal situation, our samples would lie on the diagonal where predicted equals true. But what we can also do is try to understand where the predicted labels does not equal the true label. So to do that, we have a few more imports, and we can do that. So from sklearn.metrics, we're going to import Confusion Matrix, and we're also going to import ConfusionMatrixDisplay. So this will allow us to visualize our output in a graphical manner. So let's create our Confusion Matrix. To do that, it is as simple as passing in the true values and the predicted values. So let's make a variable called predicted y. And to do this, let's pass our pipe.predict. Recall we never ran predict, so this score method has a predict and a score built in. And so here we're going to explicitly call the predict method, and we're going to do predict xtrain. And that will give us our predicted y values. And so we'll pass in y train as our true y. This is ground truth. And then we'll pass in our predicted y values as the second output. And what we get is this matrix. Oops, I meant test. And what we get is this confusion matrix. Now, this is not the easiest way to visualize it because we don't quite recall, which row corresponds to which label, and same for the columns. And so this is where the confusion matrix display comes in. So let's store this as CM, or confusion matrix. And we can pass that object to this confusion matrix display. If you look inside this method, we have our confusion matrix, which would be CM. And we can pass in display labels, which really will be this training unique values. So let's set that equal. So we'll say display labels equals, and we can pass this in. And let's see where we are with this. Okay, so recall when we see this object here, there's more we have to do to actually understand what the data is. So let's call this display, or DISP. And to render it to the screen, we just pass in the plot method. Oops, I did this again. So this should be yTest. And there we go. So we have our confusion matrix here. We can see that it's a little bit difficult to read, particularly on this bottom part. And so this is essentially a matplotlib object. So we can use our pyplot methods to improve this. So we can just set the xtix rotation equals, we can set this to 45. And let's move this down so that it's part of the plot we've shown. And then let's add let's add show. There we go. And so now we have our confusion matrix. And so let's look at what we've got. So we have levamisole. There were 2 samples in this case, and it looks like they were predicted as levamisole. And so as you can see, everything on the diagonal is where the predicted label equals the true label. But we have samples where it fell off of this diagonal. In this case, we have a sample that was predicted as phenacetin. However, it was actually cocaine. And so let's see if we can understand what was going on here. We have another case for a misclassification where the true label was paracetamol. And one way we can visualize this is using a score plot. And so let me quickly produce that from above. So we had a plot like this from early in our video series, and this is the type of plot. This is a PCA plot of all the samples colored by their impurities, PC1 versus PC2. And we can actually, I think, use this to help us understand where the samples are perhaps misclassifying. And so in this case, we see there is some confusion around the phenacetin samples with cocaine and paracetamol. So phenacetin is purple, and it sort of runs this vertical line here. And it is being misclassified with paracetamol, which is green, and cocaine, which is orange. And if you look at it, you can see that we have our orange samples that sort of interfere here. And if you can see, we have, if you look at our orange and purple, they do sort of fall along this vertical line where we can almost imagine with a model that's estimating some coefficients that it could potentially misclassify, especially these 2 points here, if the PCA is giving us anything around the chemical similarity. As well, we have paracetamol in green, which as we get to the low levels of paracetamol, so this is 100% paracetamol approaching down to low levels of paracetamol, where again, it does in a way sort of intersect our phenacetin samples. And so we can kind of understand now with this clustering of points where we're going to have some inaccuracies, where high levels of impurities, 50, 60, 70%, or maybe even 30, 40, 50 could be easily predicted because we're way away from this dense cluster. But as we have low level impurities mixed with cocaine, it does get more challenging. And I believe that's where we're going to start having some of these samples that are being misclassified. And so this is one way where we can now start to gain more insight into how the model's performing and what it's getting incorrect. So perhaps we start building either submodels or working on other preprocessors that allow us to better split apart the high and low level impurities. Maybe we build a multi-step model that determines if a sample of cocaine is highly adulterated or highly impure versus highly pure. There's ways that we actually can winnow this down into a simpler process if it really mattered. In any case, I hope this video was helpful. If you want to be notified when more videos in this Python for Forensic Chemistry series is published, let me know. If you have questions, leave them in the comments and I'll see you in the next video. Peace.